Hello there, wind energy students. Dr. John Schrage here, and I am really tired because I've been losing a lot of sleep thinking about all the important ways in which Dr. Schrage lies to his students. He tells you something that's overly simple, and then we have to go back and fix it. Well, that's actually called teaching, right? We first learn about things in kind of a simple way, and then we build on it, okay? But man, we have some really important things that we have to sort out at this point in our education about wind energy because, man, these wind profiles have been really beautiful and simple, even if they're not exactly what we observe. But part of this story has been some hidden assumptions about the fact that we had such an ideal surface that these winds were blowing over. I mean, let's just take a look at some of the hidden assumptions that would have been in like the derivation of the log wind profile or the log linear wind profile. None of which we did because, well, that would be horrible. I mean, one of our hidden assumptions was that the surface was uniform, meaning that it had the same parameters of things like the aerodynamic roughness length and the friction velocity for very, very long stretches, effectively infinitely long stretches in all direction, okay? Well, that's not exactly right. I mean, any given location where you're going to be putting up your wind farm or your weather station or whatever, you know, this way there's forests and that way there's a lake and this way it's urban and yeah, this idea that we're going to be in some, you know, effectively infinitely large forest or something is probably only going to work if we're like at sea. And as we learned from previous modules, there isn't that much wind power at sea yet. Another hidden assumption was that the surface was hard. Okay, there was a boundary between the surface and the atmosphere, and the air didn't flow through objects at the surface, but that's not true. Real surfaces tend to be porous. That means that there's sort of a fuzziness to them. The wind can, to some extent, go through the forest, albeit with a great deal of friction and so on. Yeah, that was a hidden assumption there. We weren't worried about, like, how does the flow go through this cornfield. We said, hey, this is the roughness of the top of it. That's what we're worried about. There's actually another hidden assumption here, and that is if there's terrain, like hills or mountains or something, the flow is going to just be parallel to the terrain. If the air parcel started off, let's say, 10 meters above the hill, it will flow over the hill at every place along the way being 10 meters above the hill. That's a complicated story. Actually, figuring out terrain and atmospheric sciences is a complicated story in general. But as we're going to find out in Chapter 5, that's actually not going to be the end of the world. But let's wind back here for a second. What about this business of porous surfaces, like in this sort of sparse forest I have here in this picture here? How does this notion of a wind profile even apply? Certainly down near the ground where, you know, the flow is not just experiencing the roughness of the top of the forest, but there's this whole layer that the flow is trying to squeeze through. I like my idea of like the log wind profile or the log linear wind profile. I just don't know that I think it starts at the ground. Okay, I mean, the flow below a certain height, like in the forest or in the canopy of leaves in a cornfield or a soybean field or something, that's the problem. I don't know. I mean, maybe up above I could still play this game of log linear wind profile or log wind profile or whatever. But where am I going to start? I mean, I like what your textbook says. The issue now is that the height above ground level is still defined from the surface up, and not from the often ill-defined top of this porous medium like a forest. And so the good news is there's actually a relatively simple solution to this. I mean, we can just take, for example, the log wind profile, although we could have used the equations for any of our idealized wind profiles, and we're just going to offset it by some so-called zero-plane displacement, d, where this d is going to be like how high above the ground we want to start our log wind profile. So, you know, now that's going to be a different height depending on different materials or whatever, but it's just going to be taking into account the fact that there is some height above the ground where we're going to first be starting our log wind profile. You know, like maybe some height roughly of the forest canopy, or maybe a little bit above the forest canopy or something like that, where we're going to say that's our new start to the log wind profile. Below there, something else is happening, but that's not of interest to wind power, right? You don't very often set up a wind turbine 5 meters above ground level in the middle of a forest with trees even higher than the top of the turbine. I mean, that just isn't the way it works in a wind power application. So since we're not using other things like, this will definitely have effects for like the rate of evaporation off the ground in the forest, or the rate at which heat conducts from the ground into the atmosphere in the forest. But that's not what we're doing in wind power anyway. We're only interested in what's going on above the canopy. So this zero plane displacement solves a lot of problems for us. It's not a particularly difficult thing mathematically. I mean, we just basically, subtracted off this d that got us, some height above the ground. And it's not a particularly difficult adjustment into the math and so on. Now, figuring out what this value of d is going to be could be a challenge, and your book mentions some of the challenges associated with that. But there's a bigger problem here, and that is, no matter what, this change in the surface, like now we're over a porous forest, doesn't extend forever. At some point, you are over a new surface regime. Like in this case, I've got this little isolated forest here, but it could be a much bigger thing. But at some point, it ends. We reach grassland, or an urban environment, or a dry plain, like in a desert, or we reach the ocean. And we hit the boundary with a new surface that has new parameters. I mean, over the forest, we had some value of Z0. We'll call it Z0 2 here. And there was some value of Z0, we'll call it Z0 1, over the grassland there. And in this case, actually, because it was a forest, we wanted to have a zero plane displacement, so there was a value of D over the forest, which doesn't really apply all that meaningfully over the grassland. I mean, I guess you could argue that the wind is flowing between the blades of grass, so you need a displacement of maybe a few centimeters or something over the grassland. Really, that's just not going to matter for like wind power applications. Okay, so we have two different surfaces here, but how does the flow transition from one to the other? I mean, I can picture there's some log wind profile that's appropriate over that grassland, based on its value of Z0, and its value of U star for that matter. And I can picture that there's some value of a log wind profile, some shape to it over the forest, associated with its value of Z0, the aerodynamic roughness length, and its value of U star, the friction velocity, and for that matter, its zero plane displacement D. But how does the flow get from one to the other? What causes that change along that boundary? Now, your book kind of does a little hand-waving thing and says, basically, just sort of make an assumption here that, like, there's a transition. Far from the forest, you can assume that you have the conditions of, like, the grassland or whatever. And at the forest, you can assume that you have the conditions of the forest, and then kind of taper it so that, like, some distance away from the forest, you have conditions that are starting to look more like the forest, closer to the ground. And I don't want to get too bogged down in this, because this is kind of terrible. Basically, they're just saying, start assuming the wind, like, feels the forest before it even gets there. The wind is coming from the grassland towards the forest, and it's saying, well, first let the winds near the ground start, like, acting like the forest is already there. Well, this is kind of terrible. I mean, it might not be a terribly, like, gives you wildly inaccurate ideas about how much power your wind power turbine is going to be producing, but this is pretty cheesy and not very helpful. And so I would say we can do better by what they do in the next part of this chapter, which is called internal boundary layers. If we start thinking about internal boundary layers, we can come up with a much more quantifiable way of explaining what's going on as the flow transitions from being over one regime of things like aerodynamic roughness length and U star and so on, to another. But before we do that, let's answer a few questions about our basic ideas about this and about the changes in these parameters as we move from one surface that may not be all that ideal to another surface that may not be all that ideal. Question 1. I actually have a picture in the background of a piece of geography called the Bonneville Salt Flats. You might be familiar with that. The Bonneville Salt Flats is a dry lake bed in Utah, I believe, maybe Idaho. And it's a big dry lake bed. It's almost perfectly flat. It's very, very hard. It's this salt sediments, basically. It has basically no vegetation whatsoever. A good value for the zero plane displacement over the Bonneville Salt Flats would be 0 meters, 10 meters, 100 meters, or infinity. What would we use for a zero plane displacement over such an environment like this if we were trying to, like, set up some wind profiles for this location. Make a choice from those 4 options and get some feedback before you move on to question 2.